All right, everyone. I'm very excited to introduce this week's speaker. We have Dr. Stan Mordensky. Stan received his bachelor's degree from the George Washington University. He then completed his master's at the University of Oregon. Stan received his PhD from the University of Canterbury in New Zealand, where he focused on the influence of hydrothermal alteration on the geochemical properties in volcanic rock, specifically in the Ruapehu volcano. Stan is currently finishing his fourth and final year as a Mendenhall postdoctoral researcher at the USGS. During this fellowship, he has been working on developing the machine learning tools for the next round of resource assessments. Stan had this statement in his bio that was my absolute favorite in all of speakers' bios this year. Here's the statement. In his free time, Stan walks too far, talks too much, and sleeps too little, but is always grateful for an audience who wants to hear about his research. Stan, we would love to hear about your research. When you're ready, please begin.
Thank you, Noor. Hi, I'm Stan, and I have the pleasure of sharing perhaps some controversial ideas with you today. And I should name my accomplices before I do so. But before I begin, is my screen sharing? I don't have any confirmation on this end.
Yes, it's working.
Awesome, thank you. So I work at the US Geological Survey with Eric Burns, who is the project lead for the geothermal resource investigations, John Lepore, a machine learning professor at Portland State University, Jake D'Angelo, who was once a cartographer and is now a geologist with the survey, and Pascal Caraccioli, a rising graduate student who is our intern. Now, when I say controversial ideas, I say so primarily because if you've been following the application of machine learning in the natural sciences, I suspect that you've seen some potential misuse of machine learning. And often what we see is that when there's a problem that is presented in the natural sciences, we see a neural network is applied to address a question, to make some kind of predictions. And fundamentally what's happening is these practitioners of either geoscience or machine learning are jumping straight to the deep end to these complex approaches when the natural sciences don't necessarily interface well with these complex machine learning approaches. My background is primarily in geoscience. As an undergraduate, I studied geoscience and economics, but in graduate school, I continued on through geoscience. I only returned to the mathematics of my economics undergrad education when I joined the survey, which is really just a way to say that I'm a geologist that is approaching machine learning from the perspective of a geologist. And the team that I work with is rather cautious in their approach as well. And we all take the fundamental philosophy of tackling a problem at the simplest approach first. We develop a simple model to try to constrain the effects of whatever question we're addressing. And once we understand that simple model, only then do we build complexity to try to make a better model, while at the same time retaining that explainability. So at the US Geological Survey, I should say the survey is mandated to produce semi-periodic resource assessments, hydrothermal resource assessments for the United States. And new assessments are produced as either new data or new methods become available. The most recent assessment was completed in 2008, and that assessment was dependent upon several expert decisions. Well, since then, machine learning has advanced a fair bit and presents the opportunity to apply new methods to complete these assessments. And that's where I come in. I joined the USGS 3 years ago as a Mendenhall, asking the question, can machine learning predict hydrothermal resources at least as well as, if not better than the methods dependent upon expert decisions from the most recent assessment? And spoiler, the answer is yes. And I'll go through that explanation first, but once I do, I'll move on to subsequent studies that demonstrate how we can do better. So I'll begin with something that I released earlier this year in February that demonstrates how machine learning can predict hydrothermal resources at least as well as methods dependent upon expert decisions. And in that process, I hope to share with you why we think that these simpler but nonlinear machine learning approaches work best, and how we can gauge how valuable new data are. And from this, we develop a few different hypotheses, such as that the informational value of new data should be examined to see how we can do better, and how the selection of negative sites may impart bias. The 2008 assessment was the most recent assessment completed by the US Geological Survey and was for the Western United States. Let me move my cursor around and see if this helps. This assessment predicted relative favorability across the Western US. And by relative favorability, I mean on these maps, these products of the assessment, higher favorability for a hydrothermal system is depicted in red, like here at Yellowstone, and lower favorability is depicted in blue, like the Oregon and Washington coast. This assessment was completed by gridding the Western United States into over 700,000 2K by 2K cells, in which 278 of these cells had known hydrothermal systems or known positives. Now, the remainder of these cells were not negative. They were simply classified as unlabeled. These 278 known positives were correlated with 5 input layers or input data sets, what I call features. These features are heat flow, distance to nearest fault, distance to magma, seismic event density, and stress. And although these data sets are continuous, due to the tools available at the time, these data sets had to be binned. And it's this binning where expert decisions entered the workflow. How many bins do we use? 2, 5, 8? I won't call these decisions arbitrary, but these were decisions completed by Williams and D'Angelo back in 2008. And the question then becomes, how did the choice in the number of bins influence model predictions or bias the models? Well, we can use modern machine learning to answer that question. And that modern machine learning doesn't require the use of this binning. However, modern machine learning, in this case, the application of supervised binary classification machine learning, that's just jargon, don't worry about it, doesn't require the binning. But there are challenges involved in that. Okay, the way supervised machine learning operates is by presenting an algorithm with labeled examples. The classic analogy used is training a piece of software to differentiate between emails that are spam and emails that are not spam. And you train this software to differentiate between spam and not spam by showing that software examples of this is what a spam email looks like. This is an example of what a not spam email looks like. And from that, the software will learn what words to look for, what structure to look for. You get the idea. Well, in this assessment with these data, we have positives, but we don't have known negatives. So that's one challenge in applying supervised machine learning. The other challenge is the inherent sparsity of hydrothermal systems, in that given the grid that we've applied to the Western US, we would roughly anticipate that for every positive hydrothermal system, or every positive cell, I should say, we would have roughly 1,000 cells that are negative. And that's a bit of a problem in machine learning because machine learning also operates from the perspective that we're going to try to maximize performance metric like accuracy. How often do we predict spam emails as being spam emails? And how often do we predict the not spam as being not spam? Well, with this inherent sparsity of hydrothermal systems, if we just had a dumb model that predicted the entire Western US as being negative, that model would be over 99.99% accurate, even though that model has no predictive skill whatsoever. So it's hard to maximize something that's already at an extreme. To get around these challenges, we developed a custom training strategy, actually 2 custom training strategies that subsample from the unlabeled cells the expected number of negatives that we would have per number of positives. And I say 2 training strategies, and that one was a bit more complex than the other. And if you want more details on that, I encourage you to go read the paper. But for the sake of this presentation, that's all we really need to know at this point. So we take these training strategies and we apply them to several different machine learning algorithms or model structures. And like you may have heard me say at the beginning, there's a common phenomenon in the sciences where we go straight to the deep end, or as this meme, if you can forgive the use of such, illustrates. It's common to go straight to the neural network. And the idea that neural networks are the cure-all to our problems is a bit misguided. And if you're familiar with the life of Brian, then this doesn't require any explanation. But if you're not familiar with the life of Brian, which is a wonderful satire that you're missing out if you haven't seen it. It's from the 70s, I believe. But the idea is that this man is pleading to the crowd, "I am not the Messiah, please listen." And that falls upon relatively deaf ears in the crowd, and that their conclusion is he is the Messiah. And that is how we treat neural networks in the natural sciences. So what do we do instead? Well, we take these training strategies, and yes, one of those training strategies is a neural network, but that's the most complex approach that we try. And it was the last approach that we tried. We started with the simplest approach we could find, which is logistic regression. And logistic regression at the fundamental level can be thought of as linear regression for a classification problem, differentiating a 0 from a 1 or A from B. Then we tried something called XGBoost. And XGBoost is a boosted gradient algorithm. But really, if you're not familiar with machine learning, imagine that it's a decision tree system on steroids, and that one simple decision tree is fit to the data. And then whatever is misclassified in that first decision tree is fit in a second decision tree. And whatever is misclassified from there is classified in a third. Then we tried something called a support vector machine, or SVM, with a nonlinear radial basis function. And that's somewhere between the decision trees of XGBoost and the artificial neural network in terms of complexity. So again, we tried these training strategies with these different machine learning algorithms, at least with the first 3. With the artificial neural network, we only applied the simpler training strategy because training the neural network was extremely costly in terms of processing time. And by the time we got the results from the simpler training strategy with the neural network, we didn't see compelling evidence to continue on with the more advanced training strategy. Okay, a lot of talk about what we did. Let's look at how these different systems produced prediction maps. Here we have the prediction maps from the data using the 2008 assessment and the methods from the 2008 assessment. And now here we have 7 new favorability maps using the data from the 2008 assessment, but the different machine learning approaches with logistic regression on second to the left, XGBoost in the middle, the support vector machines second to the right, and the artificial neural network further to the right. And the simpler training strategy is on the top, and the more complex training strategy is on the bottom. So as we move from left to right and top to bottom, we increase the algorithmic complexity. So when we compare the 9 different approaches, the 2 from 2008 and the 7 different machine learning approaches, we see relative agreement in these favorability maps, in that highs are often predicted as being relatively high. I draw your attention to Yellowstone, or the Great Basin, or the Salton Sea, the geysers. There is greater variability about what is predicted as being the lowest favorability for hydrothermal systems. But from the perspective of trying to produce hydrothermal favorability maps, which can be thought as being akin to prospectivity maps, we're much more concerned about what is being predicted as the highest than what's being predicted as the lowest. Because the intent of these maps is really to say, hey, where should we spend more time looking next? And that consistency is encouraging. Okay, so the methods from 2008 and machine learning methods, they're doing relatively similar in terms of maps, but which of these approaches is best? And this is where things become a bit tricky and we have to be a bit clever because the methods from the 2008 assessment, they don't predict where we do and do not have hydrothermal systems, whereas the machine learning methods do that as well as predict relative favorability. But the machine learning methods or approaches gauge performance by how well they're predicting the known hydrothermal systems as existing or predicting as hydrothermal systems. But because we don't have known negatives, we can't say that we're predicting negatives well at being negatives. And even if we could, the methods from 2008 don't allow direct comparison anyhow. So we do something a bit different. We ask, how well do each of the approaches do at predicting the known positives as being positive with respect to all the other unlabeled cells in the data set? And the way I go about doing this is by normal scoring transforming each set of predictions from each of the approaches to bring them all onto the same unitless scale. And then I pull out the predictions for the known positives. What that means is that the distribution of the predictions for the unlabeled cells is nearly a standard normal distribution. And that means a mean of 0 and a variance of 1. But the predictions for the known positives, because there are only 278 from that 700,000, those should be higher if the model has any predictive skill. So on this plot, on these cumulative distribution functions, the shaded area represents predictions for the unlabeled cells, and each of the lines represents the predictions for the known positives from the different approaches, with the idea that the positives are being predicted as more positive per approach the further to the right each of these lines, the better the model is doing. And XGBoost, using the simpler training strategy, does the best job at predicting the known positives as being positive relative to all the unlabeled cells. The second best approach is XGBoost with that more advanced training strategy. And then all the other different approaches, those from 2008, the neural network, logistic regression, they all fall relatively on top of each other. So, well, this is a bit parsimonious with what we're trying to predict, the system of, or the data that we have and the physics of what we're trying to predict. So in terms of the data that we have, in general, the more complex the approach, the more data one needs to train a good model. We only have 278 known positives. That's not a lot of data in the world of machine learning. So the idea that something that's relatively simple, the decision tree system, is doing well, makes sense from the machine learning perspective. In terms of the physics of what we're trying to predict, XGBoost is nonlinear, it's decision tree based, and that just because you have more of something, say more heat flow or more stress, doesn't necessarily mean that you have higher favorability for a hydrothermal system. Hydrothermal systems operate in Goldilocks zones of geological conditions, and that decision tree structure of XGBoost allows us to target those Goldilocks zones. So this is encouraging. And then we ask, well, which of these 5 input features is the most influential in leading to these model predictions? And in machine learning, we have many ways to measure how important each of the different features are. And I'll simplify it a bit and say that there are 2 primary categories of measuring feature importance. One is model agnostic feature importance, which really consists of shuffling the data sets or each of the feature sets sequentially and seeing if as we shuffle one feature set and then running the model again with that shuffled set of features, how much that shuffled feature influences or adversely affects the predictions for the model, with the idea that if a feature is shuffled and the model is extremely affected, well, that's an important feature. And then there's the model agnostic approaches, like in the case of XGBoost, how often is a feature used in a node? How often is a feature used in a node that influences the model predictions? These ways of measuring how important features are specific to that type of algorithm. So because there are so many different ways, I tried as many as I could. And there's a lot on this plot, I acknowledge that. But I want you to focus on the overall shape with the understanding that on the right y-axis, we have each of the 5 features used in this study. And on the left axis, we have the 9 different approaches per feature. And on each line of the approach per feature, we have the different measures of feature importance allowed for that approach, with the idea that on the x-axis, each of the measures of feature importance have been min-maxed and normalized between 0 and 1. So the further to the right, the more important that feature is, and the further to the left, the less important that feature is. And what we find is that heat flow and distance defaults are the 2 most important features, with seismic event density and stress being the 2 least important features from the 2008 assessment. So from this, we find that machine learning can do at least as well as, if not perhaps better than, methods dependent upon expert decisions like those from the 2008 assessment when we're trying to predict hydrothermal resources. But with hydrothermal data, nonlinear but simple approaches are best. And we have ways to measure how valuable the data are. And the more ways we use, the more robust that assessment is. I shouldn't say assessment, that measure is. But from this, we have a couple hypotheses, one of which is the value of new data should be examined. And really we ask this by, can we just add new data and improve model predictions? And that's what I do next. We take 2 new features from Zen 2022, shear strain rate and dilation strain rate for the Western United States. And we add these 2 features to the 5 features from the 2008 assessment. And we use XGBoost with that simpler training strategy to see how predictions for unknown positives change. And we return to those cumulative distribution functions to measure how well we're doing at predicting our known positives as being positive. So the solid red line, that depicts our predictions for our known positives using the original 5 features from the 2008 assessment. When we add shear and dilation strain rate, we move to the dashed line, and we do a little bit better at predicting our known positives as being positive. Adding these strain rates better helps us. That's not the way to say it, Stan. Adding these strain rates helps us predict these known positives a bit better. But then we ask, how can we do better still? Well, what if we remove the 2 least important features from the 2008 assessment, the seismic event density and the maximum horizontal stress? And we go from the dashed line to the dotted line. And when we do that, we're doing better still. We're better able to predict the positives as being positive. Well, that's a bit interesting. What's going on here? We are removing relevant data. I shouldn't say relevant data, geologically correct data. And yet we're better able to predict our hydrothermal systems. If you're well-versed in machine learning, this should not come as a surprise to you. But if you're a geoscientist like I am, this is a bit unexpected. But in machine learning, there's something known as the curse of dimensionality, with the idea that given a certain number of labeled examples, for us 278, you can keep adding features and your predictions will improve, presuming that each feature is of equal importance, but only to a point. And for a given number of labeled examples, as you keep adding features, performance begins to decrease. What's happening? Well, imagine another way to say this is that each feature is a dimension in a space that the machine learning algorithm is trying to draw a decision boundary in. In a one-dimensional space, the machine learning algorithm is only trying to find a point on a line, a threshold and values where greater than or less than we do or do not have hydrothermal systems. And you only need 2 or 3 points on that line, or examples on that line, to make that distinction. But if you move to 2 features, you move to a plane. And you need a few more examples in that space to draw a line now to differentiate your positives from your negatives. And what this really means with hydrothermal systems, we need to select the fewest best data layers possible for hydrothermal resource assessments. And it's not uncommon in studies that have done hydrothermal assessments in the past using machine learning to have over 10 or a dozen or 20 different features used. Really, we should be using the best but fewest layers possible, fewest features possible. The next hypothesis, how does the selection of negatives impart bias? Rather, the selection of negatives may impart bias. And this isn't a study of mine as much as a student from Portland State University with whom I've been working. And he asks this question by using data from the Nevada Machine Learning Project. If you're unfamiliar with the Nevada Machine Learning Project, the Nevada Machine Learning Project took a large chunk of the Great Basin in Nevada and took several different features and fit an artificial neural network using expert selected positives like we have used, but also expert selected negatives in their case. And what they found was substantial west-east bias, but with higher favorability in the west and lower favorability in the east. So what Pascal has done is he's taken their data, their positives, their features, and he's asked, well, how did their selection of negatives influence model predictions? And he applied our simpler training strategy, since that worked the best with the data that we had from the 2008 assessment, using their positives and their features, but randomly selected negatives that scale to the number of positives that they have, and produced his own model that doesn't have as much of that west-east bias, but still a bias. And he even went so far as to produce some favorability map using an intermediate strategy, where he again used their features and their positives and randomly selected negatives, but the negatives were an equal frequency to the number of negatives used in the Nevada Machine Learning Project. And this map had substantial west-east bias. This bias is primarily resulting from some of the feature data, like strain rate and elevation, where we have a regional trend from higher strain rate in the west to lower strain rate in the east. And in the case of elevation, we have the inverse, with lower elevation primarily in the west and higher elevation in the east. Well, from Pascal's work, we find that the Nevada Machine Learning Project, their training strategy when used with XGBoost, has strain rate as the most important feature. When he uses our training strategy with their data, elevation becomes the most important feature. But what we find is that regardless of the training strategy used, we still see this regional trend. The question becomes, okay, even with these regional trends and this west-east bias, which strategy did best? And I return us again to the CDFs. What I hadn't mentioned to this point is that Pascal used not just XGBoost with the different training strategies, but also logistic regression. We don't need to worry about the logistic regression results on the CDF, they're the solid lines. I want to focus on XGBoost, the dashed lines, and the yellow line for the artificial neural network. What Pascal found is that when he used our training strategy, which on this plot is depicted as NCI strat XGBoost, he did the best job at predicting the known positives as being positive relative to the artificial neural network in yellow and the other training strategies that use XGBoost. So the selection of choosing negatives randomly did a better job than the expert selected negatives from the artificial neural network from the Nevada Machine Learning Project. What exactly is happening here? We hypothesize that for whatever reason, the way that the negatives were identified in the Nevada Machine Learning Project, these negatives were identified due to some kind of characteristic that they exhibited. And what that really means is that there was bias in the selection of negatives, whereas the random selection of negatives across the study area allowed us to select all the different ways that hydrothermal systems can fail to exist. And it's important to remember that hydrothermal systems, again, operate in Goldilocks zones. There are multiple ways that hydrothermal systems might not be able to operate. Maybe it's not enough heat, maybe it's not enough permeability, not enough fluid. While the experts selected negatives from the Nevada Machine Learning Project probably didn't do a good job of encapsulating all the different ways that hydrothermal systems can fail. Whereas Pascal, using our XGBoost, or I shouldn't say our XGBoost, using our training strategy with XGBoost, was able to capture a greater selection of how hydrothermal systems fail to exist. So from this, we have a few questions. One is, how can we engineer better features? Because we're returning to the idea that the features, that's really the opportunity to improve these assessments, not so much in the algorithmic approach, but what information can we impart in the feature data, those input data sets, that allows us to produce the best model possible. And to that end, I turn to this comic, and that correlation should not be confused with causation, or every single person who confuses correlation and causation ends up dying. And I think this is a great example in the case of the elevation data, because the elevation data are depicting multiple signals. You have both local structure, like the basin and range, but you also have regional structure, like the trend in elevation from west to east. And when it comes to hydrothermal systems, I ask you, what do you think is more important? Do we want that local structure, or do we want that regional trend? My perspective is that local structure is of great importance, because those faults that produce the basin and range, those are the pathways along which we have potential hydrothermal fluid flow. So what Jake D'Angelo has done, what he produced, I believe, this year, was he took the raw elevation for the Great Basin and he found the moving trend across the Great Basin and produced the elevational trend for the Great Basin. He then subtracted that trend of the Great Basin and produced detrended elevation. And Pascal is using the detrended elevation with the different training strategies now. And I don't have results to show with you or to share with you, but I'll go ahead and leak now that the detrended elevation feature set is producing better predictions than the model that uses the raw elevation. Next questions. How do we address regionality, and how do we differentiate between different types of hydrothermal systems? And regionality from the perspective that, do we expect a hydrothermal system, say in the Great Basin, to look like a hydrothermal system in the Cascades or in the Snake River Plain or Texas? And these hydrothermal systems are likely to be different. Well, one way to address these questions is to focus on a specific region. And that's what I'm doing next. I'm developing the workflow for the hydrothermal resource assessment for the Great Basin that the USGS needs to have in peer review, I think by the end of fiscal year 26. And we're taking a bit of a different strategy in this case. We're trying to engineer not just better features, but also better labels or better targets. Instead of zeros and ones, or the presence or absence of hydrothermal systems, we're trying something else. So much in the same way that Jake D'Angelo found the trend for elevation in the Great Basin, Jake D'Angelo took the thermal gradient well measurements across the Great Basin from I believe 3,000 or 4,000 different wells, and he found the regional trend for heat flow, the conductive background heat flow. And when he removes that conductive background heat flow trend from these wells, we're left with the departure between the well measurements and that heat flow trend, as depicted on this map on the right, where the topographic colored surface that represents our regional trend in heat flow, our conductive heat flow. Each black dot conceptually represents a heat flow measurement from a well, with the dashed line showing that departure between the conductive heat flow and that well heat flow measurement. Well, what does this do for us? It gives us this idea that we have this continuous range in heat flow signals from slightly negative or low to extremely high. And what this means is that we now have a continuous range in targets or labels that we can use in a machine learning application. So instead of classification, that binary classification of presence or absence of hydrothermal systems, we can instead use regression. And much in the same way from the 2008 assessment, we will use other input features of geological conditions like, say, conductance or seismicity, depth to basement, strain rates as our input features to correlate with these signals of convective heat flow. And this is all part of the Ingenious project for the Great Basin. I only use 16 features in what I'm sharing with you today because that's what I had available to me when I started this work a year ago. But we're at 53 plus different features and counting, and I'll touch on that a little bit toward the end. So I hope at this point you're under the impression, this is the last meme, I promise. I hope you're under the impression that I'm not going to jump straight to a neural network. Because XGBoost was our best performer in the past, we're going to start with XGBoost. And because we're geoscientists, we're going to consider the data that we're using and that this continuous range in heat flow from low to high, what does it really mean? When we have departures in, say, okay, so departures close to zero, let's say negative 25 to 25 milliwatts per square meter from the conductive background heat flow, those are all pretty low. So we'll go as low as negative 25, and we could still call those effectively no departure from background convective heat flow, or conductive heat flow, pardon me. And we can move a few hundred up if we have if we have convection in the area, we can expect to see departures from conductive heat flow up to a few hundred milliwatts per square meter. But what does it mean when we have departures from conductive heat flow into the thousands of milliwatts per square meter? Well, rather than having hydrothermal systems in the area, it probably means that this measurement, this well measurement, is of an actively convecting system itself, given the magnitude of that signal. So because of these different considerations for what we're actually measuring, I try two different ranges of data when using machine learning. I have the all data range approach, which goes from the most negative, the negative 100, which frankly, I'm not sure what these more negative values mean in terms of what is the departure of negative 100 milliwatts per square meter below conductive heat flow. It could be, say, downflow, and we would expect that these higher convective signals mean upflow. But because I'm not quite certain what these negative signals mean physically, I exclude them from the more narrow range of signals of negative 25 to 200. And I don't just use XGBoost. I also like to use some kind of simple and fast machine learning algorithm as well. And believe it or not, go ahead and laugh, it's okay. Linear regression is considered a form of machine learning. It's a correlative function, y equals mx plus b. And I use linear regression here just to keep a baseline as to how these different data are interacting. And with this linear regression plot on the left, you will notice that there is only one. There is neither a null data nor a truncated data. Well, this is actually the all data linear regression, but the truncated data shows much the same thing. It has no predictive skill whatsoever. It has a mean of roughly 250. Oh, I'm getting ahead of myself. On the x-axis, we have the values reported by D'Angelo et al. And on the y-axis, we have the predictions from using the machine learning approach. And what we find is that the linear regression, again, has no predictive skill. The mean prediction is something around 250. And the distribution of prediction seems to be rather random around that mean. So I didn't bother to go into, I looked at the predictions using truncated XGBoost or truncated linear regression, but I do not depict them here. With XGBoost, we see a bit more promise. With all data XGBoost and truncated data XGBoost, we see somewhat of a positive relationship, although neither versions of these approaches have or fall on a one-to-one line, this dashed black line. Ideally, we would hope that, or a best performing model would have a one-to-one correspondence between the reported values and the predicted values. Although I concede that because of the differences in training ranges used in our targets, the scales of the axes are quite different. So let's go ahead and bring the scales of these axes to be the same. When we do that, we see still, yes, linear regression has no predictive skill, but all data XGBoost does not have as strong a correlative relationship between our predictions and our knowns as truncated data XGBoost. So truncated data XGBoost has a more positive relationship. What I suspect is happening here is that those extreme outliers in the all data XGBoost, those extreme outliers in those when we use the entire range of label values, those bias the predictions. And those bias the predictions in a way that do not allow us to predict the highs as being as high or the lows as being as low. When we remove those outliers, we do a bit better at predicting the hydrothermal systems, or the convective signals, I should say, across the study area. But we should also look at the maps. So when we look at the prediction maps, we see that, okay, linear regression predicts something like a third of the study area as having a high convective signal. That's not terribly useful to us because the point of these prospectivity maps, these favorability maps, is to restrict the area that we should expect to find, or we should expect to continue exploration for hydrothermal systems. Well, okay, so linear regression doesn't offer much value. We expected that. When we move to all data, we see a bit more granularity, but we still have a large percent of the study area popping up as red. With truncated data XGBoost, we have a smaller area popping up as high favorability, or as in red, and a greater part of the area as low and intermediate, and there's greater granularity as well, which that is what we would prefer to see. But let's ask, how can we inspect the performance of these models yet another way? And to that end, we ask, how well do these approaches do in predicting known power producing systems across the Great Basin? And that's what these cumulative distribution functions depict. And this is the last time we'll be seeing cumulative distribution functions. Each of these plots compares the distribution of the predictions per the three different approaches given by the shaded blue to the power production, I should say shaded blue on the left axis, to the power production in the Great Basin by these stepwise cumulative distribution functions depicted by the right y-axis. Each of the colors represents the power of production, or the temperature of production, with red being greater than 130 C, or I should say power production at greater than 130 C, yellow being power production at greater than 100 C, and the brown-green being production at greater than 90 C. We have 18 systems, 18 power producing systems, according to the University of Nevada, Reno in the Great Basin, that are producing power at greater than 130 centigrade. These lines connect that power production to their corresponding prediction in the cumulative distribution function for the predictions. And what we find is that it's not truncated XGBoost that restricts the, say, a quarter of our power production to the smallest percent of the study area. In the case of all data XGBoost, 1.6%, or 50% of our power production to 2.5%. It's not truncated data XGBoost that does the best job at restricting, but all data XGBoost. So all data XGBoost does a better job at predicting our power producing systems. Why is that? Well, although these outliers in label values are outliers that bias truncated data XGBoost, these outliers are power producing systems that hold valuable information. So we ask, what can we do to reduce the effect of the outlier of the outlying effect of the label value, but still retain the valuable information of that example? To that end, we've turned to ordinal regression. If you're not familiar with ordinal regression functions by categorizing different ranges of label values. In this case, I'm using -25 to 25 as a 1, a departure from conductive heat flow of 25 to 50 as a 2, 50 to 325 as a 3, 325 and greater as a 4. So we're changing those label values based with consideration for what those departures from conductive heat flow are, but we're going to use these categorical label values as our targets instead. And there is a data-driven way to go about choosing these heat flow boundaries for these categories, and that's by running simple models and seeing where loss or error is minimized as we've tried different ranges of heat flow boundaries. And I've done exactly that. Now, this is still very much a work in progress, but early results are encouraging, and that we're further reducing the areas of the Great Basin that we will predict as having the highest resource favorability. And we're doing a decent job at predicting our highs in red as high and our lows in blue as low. This is just a cross plot, but for categorical or ordinal regression, with the reported convective signals from D'Angelo on the x-axis and our predictions on the y-axis. But again, this is pre-decisional, so I won't treat any of this with too much consideration at this time. All right, at the start of this subsection, you heard me say that we have over 53 different features. We know that we need to choose the best features possible, and that's a bit difficult in the case of these features, even with just these 16 that we've used in this study. We have considerable correlation. We're working to identify which features are the most relevant for what we're trying to predict, as well as the correlation each feature has with the other features, so we can select the fewest and the best, and that also remains a work in progress. So, in conclusion, machine learning works if given proper consideration, at least as well as methods dependent upon expert decisions, and can possibly do better. But to do that, we need to select the best, fewest data layers possible. And we need to make sure that we give proper consideration, not just to our positives, but also to our negatives. The next step in the research process really involves engineering the best features possible. And I'm also starting to play around with the idea of Monte Carlo cross-validation, but that's a subject for another time. Thank you. I believe, yep, acknowledgements and references, but I hope you have questions. And I believe I saw many questions pop up as I was presenting, so let's have them.
In the meeting chat, we have a few questions, and please feel free to ask out loud, but Herman Levitt had 3 questions. Would you like to ask them, Herman? Or I can read them as well.
Yeah, please. I asked the question during the very important and very interesting talk, I have to say, presentation. So the last one, what I have was on slide 8, you had on the right side a map of this area in Nevada, and there were a couple of elliptical features in. I guess these are artifacts out of the process, and I was wondering where they came from.
I beg your pardon, which slides were these?
38.
Oh, yes. Oh, I know exactly what you're talking about.
Sorry.
Oh, no, you are touching on a frequently occurring topic of conversation within our group. So these ellipses that we're seeing bleed through, one of the most important features in these models is distance to magmatic bodies, which is curious to us because we really don't have too many locations in the Great Basin where we have shallow magma, that we say we have shallow magma. And when I say shallow magma, I mean evidence of, I believe it's quaternary eruptions or geophysical data to say that there is magma in the shallow subsurface. And although we don't have, I don't really want to give a number because I'm sure it's going to be wrong whatever I say, but I'm going to go ahead and venture that we probably have 20 or 30 different sites across the Great Basin that we say, yep, there's probably shallow magma here. And despite that, we have such a low frequency of these points across the map, the algorithm, for some reason, is saying that this distance to magma is the most important. And because we don't have too many of these points across the study area, these ellipses are really coming out. And we're hoping that as we move to ordinal regression, which I'll go ahead and jump to that, and as we move to selecting the best features, these artifacts will fade away.
All right, I see. Okay. You have not tested it yet, I guess, all right?
Well, this is a prediction map using ordinal regression, and the ellipses, you can see, I can make the case that we can see a boundary here, but it's not nearly as pronounced with the maps that use the raw convective signal.
Very prevalent, yeah. Should I also ask my second question, I think, which came across, and actually you partially answered it as we went through the presentation, that was a correlation between the elevation and the strain. And I think that is quite interesting because in the basin ranges, we are in an extensional system, and the ranges are basically a result of the extension, so of the strain rate. So is there a correlation? I understand later on you did a great job, or your colleague, on on taking the let's say lithospheric trend out of the system because you have regional uplifts. But can you refine on that? Because I think there is a really strong correlation between the actual strain rate in the system and the fault block uplift. So have you looked in this kind of approach?
It's something we're looking at right now. And by we, I mean Pascal, our student.
Mm-hmm.
He's running these models using, instead of just raw elevation, he's using models that use the elevational trend and the detrended elevation, in addition to all the other features used from the Nevada Machine Learning Project, including strain rate. And the hope is that once we separate elevational trend and detrended elevation, that the model is going to place greater importance on detrended elevation and less emphasis on elevational trend. And we saw that when Pascal started using our training strategy rather than the Nevada machine learning training strategy, strain became a less important feature. So if there is correlation between elevational trend and strain, hopefully by using our training strategy and this detrended data, the strain and the elevation trend will fall to the background. But there's also the consideration that many of the known hydrothermal systems in the Great Basin are found in the West, in the area, I'm going to jump to another slide, the area of higher strain. See, I think it's the next slide. Yes, here, where on this map, we have positives in red and negatives in white. But most of these positives are in the area of higher strain. So I still expect we're going to see some kind of relationship between strain and hydrothermal systems. But by pulling out the elevational trend from the regional trend of elevation, like you say, is correlated with strain rate, we're hoping that we're going to allow the algorithm to create a better scenario that it's able to process well. Which is more important here, the regional strain rate or the local topography, the local structure, I should really say.
Yeah, I'm after the local structures, and at the end of the day, because you can pinpoint very nicely down where you have the highest heat flow or the highest fluid flow, because there's a huge conductive component. And the western part is, I think, also the area where you have high critical mineral concentrations.
I believe you're right.
Yeah. Quick comment. When you talked about the elevation, have you guys also looked at the gravity data, corrected or uncorrected data in that area? Because elevation, what crosses my mind is a boogie corrected gravity, which takes out the elevation in a way, but gives you a better signal on the local basement distribution, things like that.
Interesting. We haven't done any work on gravity, but we've discussed how geophysical data like gravity could be used similarly to what you're talking about, but in a bit differently, I should say, in that, well, often what we find is that with local structure, we see the worms, forgive me, I'm not a geophysicist. Can I call them the gravity worms in the Bouguer data that correspond to faults? And we're asking, well, is there a way that we could engineer the gravity data so that we could turn these worms into lineaments that would correspond to the fault data? Because we know that we can't always map faults in their entirety, but the gravity data don't lie. So if we could engineer the gravity data to be representative of structure instead of just using mapped fault structure, we might be able to produce a better model in that respect.
I think it would work because it's responsive to the exhumed basement, and which you see in the ranges more than in the basins, which are filled with young light sediments. So I think it could bring out very nicely the structure without really touching the faults, but you can delineate them maybe better on that way. That's maybe an idea.
Understood. Well, I think we're of like mind, although I need to tread lightly here.
Yeah,
We're
yeah,
talking
sorry.
on a subject that is not really mine as much as Jake's, and Jake is a close colleague of mine, but I don't want to inadvertently promise that he's going to be doing anything that he hasn't necessarily agreed to at this point.
Okay, thank you so much for the conversation and for the presentation.
Thank you. Those were great questions.
Stan, I have a question too. It's about cursive dimensionality. Instead of removing features that seem to be less helpful, have you considered running something like PCA, where you reduce the number of features, but you still keep them in consideration?
This is, yes, we haven't, it's something that I've even done using the ingenious data with the regression approaches. And it will produce a better model, but we would like to retain the explainability of whatever we end up producing. So I'm still refining the workflow for regression. Once I finalize that workflow, I'm going to be trying using a narrow range of standardized feature values, but I'm also going to be trying a PCA version of those features and seeing how much the models are different. And what I'm hoping is that that dimensionality reduction isn't going to have too much of an effect on producing a better model, because I'm rather keen to be able to produce something at the end of the day I can give strong attribution as to how much, say, fault distance or conductance plays in these predictions rather than PCA. Because when you do dimensionality reduction, which is a perfectly legitimate method, you lose the ability to attribute how much impact each feature is having as easily as if you hadn't used PCA. But that's, yes, it's something we've been discussing, but we're not quite keen on it just because of the philosophy of our group.
No, that makes sense. We have time for one more question. Does anyone have a question that they are burning to ask? All right, it seems quiet. Well, thank you so much, Stan. This was excellent. It was very informative. Thank you for sharing your research with us.
Thank you for the opportunity. It's a pleasure.